All right, well, we got to get started here. So, um, on the test, there's that ozone question, but it was I didn't change it in the parentheses. I put O2. I'm not sure if you did ozone. Let me know because it gives you a different number. With O2, oh yeah. With O2, there's going to be a total of 6. Was it still not on? Total of 6 unique ones. Okay, does that answer the question, Kiana?
Yeah, but on the scan it says C is the correct answer.
How many is C?
3.
3? Oh, that's wrong. I'll have to fix that. It's not 3. If it's ozone, it's 10. For O2, it's 6. Okay, were there any other? Let me do this. Questions? All right, sorry for the delay there, but we'll get started now. So what we're going to do experiment 17. Actually, we already finished 17, except for one thing. Let's see. What did I do with it? So last week we did the first part of experiment 17, but we didn't quite finish it. We're going to do the second part as a demo experiment, and what I'll do is I'll do these sometime later, but these are all double replacement metathesis style reactions. So in the second part of this, we'll take some lead-2 acetate, mix it with sodium carbonate. What forms in this reaction here? So in double replacement or metathesis, we just swap the ions. So this is going to be lead with carbonate and sodium with acetate. So we form lead-2 carbonate and sodium acetate. Lead-2 carbonate's a white precipitate, so we should get a white precipitate in this reaction. What happens if we take lead-2 acetate and sulfuric acid? What forms here? Yeah, lead-2 sulfate and acetic acid. Lead-2 sulfate is a white precipitate also, and will precipitate out. How about lead-2 acetate and sodium hydroxide? What will form there? Just swap the anions. So rather than lead-2 acetate, it's lead-2 hydroxide. Lead-2 hydroxide is a white precipitate that's going to precipitate out. And what's the other product? Sodium acetate. Okay. What about lead-2 acetate and aqueous ammonia? Here we can't swap the anions because there's no anion there. And so with aqueous ammonia, it doesn't seem to fit the pattern. But what you have to realize is aqueous ammonia is a weak base. And what do weak bases do? They hydrolyze water. And when they hydrolyze water, ammonia plus water forms what? ammonium and hydroxide. But it's weak, so it only partially hydrolyzes water. And so about 1% of the ammonia will react with the water to form ammonium and hydroxide. So, but you know, that 1% is enough. All we need is a tiny bit of hydroxide, and that tiny bit of hydroxide is going to form lead-2 hydroxide, a white precipitate, and ammonium acetate. Ammonium acetate's not a driving force. And so with aqueous ammonia, we treat aqueous ammonia like ammonium hydroxide because it's 1% ammonium hydroxide, 99% aqueous ammonia. But when we go to the store to buy it, you know, you're just going to buy it as aqueous ammonia. It's 99% aqueous ammonia, 1% ammonium hydroxide. If you try to go to the store, the chemical store, to buy ammonium hydroxide, you're not going to get it. You're just going to get, you know, 1%. 1% doesn't seem like much. It's actually less than 1%. And so in the equation itself, we leave it as ammonia and water because that's actually what you're going to get. You're going to get ammonia and water, and there's a tiny bit of ammonium and a tiny bit of hydroxide in that, and it's enough to react in a metathesis reaction. Okay. So we'll do those later. We're going to do experiment 18 today. And so those are metathesis reactions. These are redox reactions. Redox reactions have a totally different driving force. What's the driving force for redox reactions? More active to less active? What else? There's another way of phrasing that. Kind of. We talk in terms of oxidizer, oxidizing agent, OA, or reducer, reducing agent, RA. And the driving force for redox typically is a stronger oxidizer to a weaker oxidizer, or a stronger reducer to a weaker reducer. Oxidizers, often called oxidizing agent, OA. And so stronger OA to weaker OA, stronger RA to weaker RA. That's the driving force for redox reactions. Here. So let's look at oxidizers and reducers next. Can you hit the mute button? Sorry, it's on, or yeah, close it, should be all right. So, when we look at the redox strength chart here, you should know F2. What is F2? Fluoride or fluorine? F2. Fluorine or fluoride? Well, a lot of people had it mixed up today, so I'm just curious. Fluoride is the ion. Is F2 an ion or just the element?
It's fluorine.
It's fluorine. What is this? F minus. Fluoride. Are they the same thing? No, they're totally different. Totally different. Fluorine is very aggressive. What? It's a very aggressive oxidizer. And so we have our oxidizing agents on the left side. And what oxidizers do is they take electrons. So fluorine's extremely aggressive oxidizer. It takes 2 electrons to form fluoride. Excuse me. Most of the species on the right side of the periodic table are oxidizers. They take electrons, except the noble gases. Are the noble gases very reactive? No, they used to call them the inert gases because they're so unreactive. And so what fluorine wants to do is it has 9 electrons. It wants to gain 1 more electron to get 10 electrons. So each fluorine wants 1 electron. And once it has 10 electrons, then it's isoelectronic, the same number of electrons as neon, and neon's stable. And so each fluorine wants to gain 1 electron. We have 2 of them, so it'll gain 2 electrons, and it'll give us fluoride. Fluoride has 10 electrons, it's quite stable. Fluorine has 9 electrons, quite unstable. And so there's a conjugate relationship here. The conjugate relationship is if one side is very unstable, very reactive, the other side is quite stable. And so in terms of redox, fluoride is very stable. It doesn't want to give up electrons. So once fluorine gains those electrons, it stays. Fluorine doesn't give them up. And so we have one chart for both the reducers and the oxidizers. So at the top of the oxidizers is fluorine. But fluoride would be at the bottom of the reducers. Fluoride would be the worst reducer. Fluorine is the most reactive. Fluoride is the least reactive. What's the most reactive reducer or reducing agent? You need to memorize this. Fluorine, F2, and lithium. Lithium is the strongest reducer. And so reducers lose electrons. So we look at lithium and we go backwards here. Lithium is going to give up electrons to form lithium ion. That means lithium doesn't hold on to that electron very tightly. Therefore, lithium ion is not going to aggressively seek electrons. And so what we have is we have a very powerful reducer and a very weak oxidizer. So lithium ion is the weakest oxidizer on the chart. And so the seesaw relationship is the same, except on this side, the lower we are, the stronger. And so a strong reducer, weak oxidizer. So let's take a look at some of the oxidizers on the chart and see what we have. So fluorine wants 1 electron. You can gain it, and then it'll form fluoride. Oxygen, here we have ozone. Oxygen has 8 electrons. It wants 10 electrons like neon. And so each oxygen should gain 2 electrons. But here we have 3 oxygens, and we're only gaining 2 electrons here. So what's going on? Well, ozone is a little bit different as far as its Lewis structure goes. What's the oxidation state of ozone? Well, elements in elemental form, like ozone, are going to be 0. They have an oxidation state. Fluorine has an oxidation state of 0. Fluoride has an oxidation state of -1. But ozone, this is the average oxidation state. Sometimes we don't want the average. Sometimes we want to know the individual oxidation states. And so we should take a look at the individual oxidation states here. So ozone has 3 atoms times 6 valence electrons each. That gives us a total of 18 valence electrons. And then to draw the Lewis structure, we have 2 choices. We could do a ring structure like this, or we could just do a chain structure like this. This ring structure is highly unstable. A 3-membered ring like this is forms a triangle is going to have a weird bond angle. The weird bond angle is going to be 60 degrees, meaning that this is unstable. So we should try to avoid this if possible. And so this would be a better structure. And then we have 18 electrons. We've used those many. So we complete the octets to the terminal atoms first. And that takes care of 16. Then we have one electron left, one electron pair left, and that will go on the center atom. But what's wrong with this structure? Do you see a problem with this structure? Yeah, the one in the middle doesn't have an octet. We can fix that by creating a double bond. If we create a double bond here, we'll take a bonding pair, make that, a lone pair, make that a bonding pair here. Okay, now all the atoms have an octet, but something still doesn't look right. What doesn't quite look right? The bonding doesn't quite look right, does it? And so we should take a look at formal charge. Do you guys remember how to count formal charge? What's the formal charge on this left oxygen? One, two, three, four, and then half the bonding, 5, 6. Formal charge is 0. What's the formal charge on the middle oxygen? 1, 2, 3, 4, 5. It's supposed to have 6, and it has 5, so it's a short one. And then this end one has 1, 2, 3, 4, 5, 6, 7. It has an extra electron. Those oxygens are supposed to have 6. So even though the average oxidation state is 0, the oxidation states aren't all 0. And so sometimes it's better to look at the individual oxidation states than just averaging them all, because you can see more about the reactivity of these. And there's going to be a resonance form for this. Looks like that. All right, this oxidation state for, this formal charge. For oxidation state, it comes out the same. So when we count the oxidation state, it's the same. 1, 2, 3, 4, 5, 6. The oxidation state comes out 0. 1, 2, 3, 4, 5. The oxidation state comes out plus 1. And this one will be 1, 2, 3, 4, 5, 6, 7. This is going to be minus 1. So these are the oxidation states. And then in the green, we have the formal charge. So what oxygen in ozone wants to do is it wants to gain 2 electrons. And in this particular example, not all of them do. And so we start off with ozone, and actually only one of the oxygens gains 2 electrons. That one oxygen that gains 2 electrons ends up in water, where the oxidation state went from over there, an average of 0 to minus 2. The oxidation state of oxygen in water is minus 2. And the oxidation state of oxygen in O2 is 0. So 2 of the oxygens went to 0, or stayed 0, and then one of the oxygens went to minus 2. Okay, now O2 itself can gain electrons to go to 2 minus, and go from 8 electrons to a total of 10 electrons, like neon. All right, so that's fluorine. Number 2 is ozone. Number 3, what's this? When you look at number 3 there, it looks like two sulfates, like a disulfate. But let's talk a little bit about the structure of that. What is this pen? So if I take a look at sulfate, I'm going to do sulfate with the octet, not with the expanded octet. Do you remember the formal charge? What it is? The formal charge on each of these oxygens is minus. And the formal charge on sulfur is going to be +2. Formal charges I'll circle. The oxidation states are counted differently. The oxidation states on each of these oxygens is -2. And the oxidation state on sulfur is +6. For formal charge, we count the electrons, assuming 100% covalent bonds. For oxidation state, we count the electrons, assuming 100% ionic bonds. And so that's going to impact the bonding electrons here. So if I look at this oxygen here, for formal charge, we assume 100% covalent, that is sharing. And so there are 2 electrons in this bond here. If they're shared 50-50 equally, then 1 electron goes to the oxygen, the other electron goes to sulfur. So if we split the bond in half here, that gives this oxygen 1, 2, 3, 4, 5, 6, 7 electrons. Well, oxygen normally has 6 valence electrons. And since it has 6 valence electrons, it has an extra electron. That gives it its -1 charge. And we say oxygen has a -1 formal charge. That's the green. For the red, we assume 100% ionic bond. So rather than covalent, we assume an ionic bond. An ionic bond, the more electronegative atom takes all the electrons. And so what's more electronegative, oxygen or sulfur? Oxygen's more electronegative, so oxygen takes both those electrons away from sulfur. If oxygen takes both these electrons, then we recount 1, 2, 3, 4, 5, 6, 7, 8. Oxygen ends up with 8. It's supposed to have 6. That gives it its -2 oxidation state. Now these are apples and oranges. So when we're looking at the number, if somebody says, you know, what's the biggest orange, and you say the biggest apple is this, you know, but I wasn't asking about apples, I was asking about oranges. We can't compare. We don't cross compare ever. We compare red with red only and green with green only. Otherwise, it doesn't make sense. And then we can get some insight into it. Well, if oxygen takes all the electrons, red, then sulfur is left with no valence electrons. It normally has 6 valence electrons, so that's why it ends up at +6. So that's sulfate. Now, if we make a disulfate, we could link these 2 together like this. These terminal oxygens are the same. You know, they have 3 lone pairs, all of them. But what about these bridging oxygens here? What are the oxidation states of these bridging oxygens? The formal charges are 0 here because it's 0 because it's 1, 2, 3, 4, and then half is 5, half of this is 6. So 6 electrons is supposed to have 6 electrons. So the formal charge is 0, but what is the oxidation state on this oxygen here? So sulfur versus oxygen, who's the winner? Oxygen. So that's 2. 1, 2, 3, 4, 5, 6. Oxygen versus oxygen, who's the winner? It's a tie, so we're going to split it. So it goes 1, 2, 3, 4, 5, 6, 7. How many valence electrons does oxygen normally have? 6. So this comes out to minus 1. And we look at this oxygen as the same. This comes out to minus 1, whereas these terminal oxygens are all minus 2. Minus 2 is happy, because minus 2 means oxygen has 10 electrons like neon. But minus 1 isn't as happy, because minus 1 means it has 9 electrons like fluorine. So these are more fluorine-like than this one. This is more neon-like. This is more fluorine-like. Is fluorine a stable element? No, what does fluorine want? Fluorine wants another electron. And so this bond here is called a peroxide bond. And peroxide bonds are inherently unstable. They're very weak. Not only that, they want one more electron. So what's the oxidation state on sulfur? The oxidation state on sulfur is, well, winner take all. So sulfur ends up with no electrons. So how many electrons did it originally have? 6. How many does it end up in this structure with? None. And so how many did it lose? 6. So this plus 6. And sulfur. There's a peroxide bond. Now the rules for oxidation state are useful, but sometimes it gives you the wrong answer. So use the rules for oxidation states to tell me what the oxidation state on sulfur is based on this. We have 8 oxygens at minus 2 each. So 8 times minus 2 gives us minus 16. Minus 16 plus 2 times x. X is the oxidation state on sulfur. Minus 16 plus 2 times x is equal to minus 2. X is equal to plus, well, oh, there's another way of doing it. This is minus 16 plus 14 gives us minus 2. Plus 14 divided by 2 gives us plus 7. And so based on our rules for oxidation state, the oxidation state on sulfur here is plus 7. But there's a problem with plus 7. What is the problem with plus 7? Oh, it's incredibly unstable because the normal oxidation state range for sulfur is between plus 6 and minus maybe this is not, maybe it's hard to visualize. Do you know where I get the normal oxidation state range? I get it from these. The Lewis symbol. The Lewis symbol for sulfur shows 6 valence electrons. So the normal range would be going to an octet in which I add 2 electrons. If I add 2 more electrons here, I'll get an octet, and that's -2, or 2 minus. Or I'll strip all the electrons off. If I strip all the electrons off sulfur, then what charge do I end up with? +6. So I get a +6 charge when I strip off all the valence electrons off sulfur. So in order to get a +7 charge, I must have taken off what? I must have taken off not a valence electron, but an inner shell electron. What are inner shell electrons called? Core. I must have taken off a core electron, but the problem with taking off a core electron is it takes like 10,000 times more energy than a valence electron. So if you, was it 10,000? You know, well, it takes, yeah, up to. And so it's not likely to happen. So in other words, if you were to follow the rules for this, then we get sulfur in a very unusual oxidation state of +7. And +7 is losing a core. So it turns out that this is a peroxide. In the peroxide, 6 of the 8 oxygens are -2, 2 of the oxygens are -1. Well, what's next here? Do you recognize this one? This is hydrogen peroxide. In hydrogen peroxide, we got to assign the hydrogen first at +1, therefore oxygen's -1. So then we go on to this one. What's this one called? MnO4 minus. Permanganate. Why does permanganate want electrons? We know why oxygen wants electrons. It wants to be like neon. Fluorine wants electrons. It wants to be like neon. But why does permanganate want electrons? In fact, permanganate has an extra electron here. Do you see that? It's got a -1 charge. And so isn't it already? Isn't that enough already? When we look at the oxygens, we have 4 oxygens. That -1 charge goes on the oxygen. And these 4 oxygens are -2. So they'd be like neon with 10 electrons. And so why does permanganate want electrons? Permanganate wants electrons because of manganese. What's the oxidation state of manganese in permanganate? +7. +7 is very electron poor. And so permanganate wants electrons. Manganese is +7, and in this particular case, it's going to gain 5 electrons. So if we go from +7 plus 5 negative electrons, what does manganese go from? It goes from +7 to +2, gaining 5 electrons in the process. So that's it. So high positive charge on manganese. What about this one? What's this called? Lead. Not lead 2. Lead 4. So like +4, +5, +6, +7, those are pretty high positive charge. You know, that's going to want electrons. This too. This is a lead 4 ion. Lead 4 ion. It's going to take 2 electrons to go to lead 2. Lead 2 is quite a bit more stable than lead 4. Chlorine. Chlorine's on the right side, so it wants to be like argon. So chlorine has 17 electrons, gains 1 each. It'll give 18 electrons like argon. What's this one called? Chromate? Chromate? No, chromate actually looks a little bit different. Do you know chromate is what? CR. O4. What's the charge on chromate? Two minus. This one looks different. We don't call Cr2O7 2 minus chromate, we call it dichromate. But what's missing? If it's dichromate, something's missing. What's missing there? And what's missing is the peroxide link. So to form a more stable link here, we lose an oxygen. So if we were to link up two chromates, we'd normally have to form a peroxide link. You put the two CrO4 side by side, we're going to get Cr2O8. But instead we get Cr2O7. We lose one of the oxygens so we can form a stable bridging oxygen, like water. You know, water is a bridging oxygen there. And not a peroxide. And so chromate is CrO4 2 minus. Dichromate is Cr2O7 2 minus. Not quite two chromates. It's two chromates minus one oxygen. Well, anyway, what's the oxidation state on chromium in dichromate? Can you see? Manganese is +7. What's chromium in dichromate? +6 is correct. And so even though it has a -2 charge, we still call this electron poor. A lot of people, they see a -2 charge, how can that be electron poor? Well, it's electron poor because when you look at chromium's oxidation state, it's +6. That -2, the extra electrons went on oxygen. And so oxygen is just happy as is. The chromium isn't. And so that makes that a powerful oxidizer, dichromate. And then we go on to, what's this one here called? Yeah, manganese 4 oxide. Manganese 4 oxide +4. You know, there aren't, how many +4 cations are there? Lead, tin, manganese? Not that many, and they're quite unstable. The higher the charge, the less stable they become. Oxygen, oxygen's on the right side, so that's going to want electrons here. So oxygen is the prototypical oxidizer. Oxidizer comes from oxygen. Oxygen is the most common oxidizer around. It's not the strongest, but It's the most common. Then we have this one. IO3 minus is called iodate. What's the oxidation state of iodine in iodate? If these aren't fast, you should try to get some more practice, because it isn't really all that hard. You just need more practice. You should be able to do these in your head by now, the oxidation state. So there's some tutorial problems and there's some additional homework problems you can do. Minus 2 times 3 is minus 6. Minus 6 plus x gives us minus 1. X is equal to plus 5. And then bromine's on the right side of the periodic table. Nitrate, minus 2 times 3 is minus 6. Minus 6 plus x gives us minus 1. Plus 5 again. This is nitrate and acid. There's silver ions. Silver ions turn out to be a pretty decent oxidizer. You have to be careful with silver salts. Silver ions can easily oxidize your skin, your flesh, your eyes. So if you spill silver salts on your skin, you'll know. Because what happens is it oxidizes your skin and then deposits tiny crystals of silver. These tiny crystals of silver look black. You know, as the crystals grow bigger and bigger, then they're going to look silver. But tiny crystals of any metal look black. They absorb all light. And so the problem is that the silver ions penetrate your cells, and the silver gets deposited inside your cells, not on the surface, unfortunately. So it doesn't wash off. So you can easily tell when you've spilled silver salt on your skin, because you'll have black stains that don't wash off. Eventually the black stains will come off as your skin sheds. You know. I had a student that in Chem 4 that spilled a lot of silver nitrate solution on their hands. And they came up to me after lab and said, I've been washing my hands for 20 minutes, but the stains won't come out. And I said, they aren't going to come out. It'll take, a week or so, and then they'll disappear. But they had an important job interview right after lab, and so they're very stressed about it. But anyway, watch out for silver ions. I mean, it's not the strongest oxidizer, but it can easily oxidize your skin as well as nitric acid. When you spill nitric acid on your skin, it forms NO. This NO complexes with your blood, the iron, and forms yellow stains. So yellow stains with nitric acid, black stains with silver nitrate or silver salt. Those are common. Then we have iron 3. Iron's relatively high charged. It wants an electron, at least one electron, to go to iron 2. Then we have oxygen. Wait, we had oxygen before, so why do we have 2 oxygens? Well, if we have 2 oxygens, then pick the stronger one. Which of these is stronger? Well, the one that's stronger is the one that's closer to fluorine up here, so this one's stronger, so ignore this one. But why write it twice? The reason it's written twice here is not because of it as an oxidizer. It's because of the conjugate reducer. The conjugate reducers are the same. No, they aren't the same, because when I look at this conjugate reducer, it's water. When I look at this conjugate reducer, it's hydrogen peroxide. So they form different products. And the reason why it appears twice here is because we have 2 different reducing agents. We have hydrogen peroxide as a reducing agent versus water. And it turns out hydrogen peroxide is a better reducing agent than water. And they both form the same product, oxygen, here. And so that's why it appears twice over here. But when it appears twice, pick the stronger of the 2. Then we have iodine. So a pattern: fluorine, chlorine, bromine, iodine. And then copper 2 ions. And then sulfate and acid, or sulfuric acid. Tin 4, high charge. Sulfur. Sulfur is on the right side, but not nearly as strong as oxygen. Oxygen is much better. Sulfur doesn't occur as diatomic, so it's not S2, it's just S. Unlike oxygen. They're in the same family, though. And then we have acid, normal acid H+, and then metal cations like lead 2, tin 2, iron 2, zinc 2, aluminum 2, and then eventually we get to the weakest. The weakest one's lithium ion, but it might not look like the weakest because we have this subchart here. Now look at the subchart. At the bottom of this chart is water. And so it looks like the weakest on the left is water, but that's wrong because this chart has to be positioned based on these numbers on the right. And so water is not actually the weakest. Lithium ion is still the weakest at -3. Water is at -0.8. If we look at where -0.8 fits on the chart above here, it fits here. I put these 3 dots here because that's where water goes. Water goes in between zinc ion and aluminum ion at -0.8, closer to the zinc ion. So water is a better oxidizer than aluminum 3+, but a worse oxidizer than zinc 2+. In general, water is very unreactive. You know, just like these metal cations here, unreactive in redox reactions. So those are the oxidizers. Then we'll take a look at the reducers. The reducers, the strongest is lithium, potassium, sodium's up here. The group 1 metals are good reducers. They lose electrons easily. So the species on the left side lose electrons. We have calcium, magnesium, group 2, group 3, aluminum, zinc is transition metal, pseudo group 2, iron, transition metal, tin, lead. All these metals are good reducers. They're electron rich. And them being electron rich, they can go backwards here to become lead 2 and 2 electrons, or tin 2 and 2 electrons, etc. And then we have hydrogen. Hydrogen's an excellent reducer as well. So these are all strong reducers. And then we have H2S. H2S is a much better reducer than H2O. H2O is really hard to lose or take electrons from. And so here's H2O's up here, here. So it's hard. H2S is much easier. So it's a bigger sulfur. Tin 2 can lose electrons. Sulfur dioxide can lose electrons. Copper, iodide, hydrogen peroxide, iron 2, silver, nitric oxide, bromide, iodine, water, etc. So those are the reducers, with the strongest being fluoride up here. So let's take a look at what we're doing here. We have 3 metals here. Metals are good reducers. Metals can give up electrons. Reducers are going to lose electrons and undergoing redox reactions. And we have 3 metals here. Copper is pretty recognizable. This is copper, the kind of an orange color. Lead is kind of a black color. Do you see that? The dark gray to black color. And then zinc is a light gray here. This is zinc, light gray, silver color. All right, what we're going to do here is we're going to block out the lead. This to just prevent lead poisoning. And then we're going to, this is a typo here. This is not lead 2 sulfate. Lead 2 sulfate is a solid, insoluble solid. We're not going to be able to make a 0.1 molar solution of that. This is supposed to be lead 2 nitrate or lead 2 acetate, one or the other. But it doesn't matter because we're not going to use either one. And so omit all the lead. Instead, what we're going to do is we're going to just take copper 2 sulfate and mix it with some zinc. So to do that, we'll just get a chunk of zinc. There's sandpaper in here. Don't bother sanding any of these metals. They'll react faster if you sand them, but you know, there are people who are sanding the lead and making lead dust. Do you want to touch lead dust or inhale lead dust powder? No. So don't sand any metals. If I see somebody sanding metals, I'm going to stop you from sanding them. But every semester, not every semester, but sometimes you'll have somebody sanding the lead. Okay, so all you do is get a piece of zinc, put it in a test tube. So I'll get that. And then back there, we're going to put a squirt or two. One squirt of those plastic pipettes is about 1 milliliter. 2 squirts is 2 milliliters. So we'll put 1 or 2 squirts of copper 2 sulfate solution in here. And then we're going to look at what reacts. So I inventory the solution. I have what in solution? Well, I have zinc metal here. Well, zinc metal is a reducer stuff. I have copper 2 ions. Just scroll up here. Copper 2 ions, and I have sulfate ions and water. Water is so unreactive. I mean, you know, water is way down here in terms of oxidizer. And so copper 2 and sulfate are much stronger. And then water is way up here in terms of reducer. It's way up here. We can't use this water here because I need sulfur dioxide. It's the sulfur dioxide that's primarily reacting here. And so zinc is going to be much better. Out of copper 2 and sulfate, which one's stronger? Copper 2 is stronger. And if I'm going to use sulfate, then I also need this. What is this? H plus. In terms of Bronsted, would that be Bronsted acid or Bronsted base, H plus? Or Arrhenius? Yeah, this is acid. Was there acid in there in the mix? Not in this test tube. That's in another test tube. And so this test tube only has copper 2 sulfate and zinc metal. There's no acid. If there's no acid, then it doesn't react as strongly. Nonetheless, copper 2 is stronger, and so we expect this to react. Now, this reaction, I'm going to use the zigzag method. Let me tell you what the zigzag method is. Zigzag method is copper 2 reacts with zinc here. So this is my zig. And this would be my zag. The zinc is going to go to form Zn2 plus. So we're going from copper 2 to zinc 2 plus. Now, the driving force is stronger oxidizer to weaker oxidizer. So copper 2 is a stronger oxidizer. It's closer to fluorine than zinc 2. So this is what we call downhill. There's a driving force here. So when copper 2 reacts with zinc, zig, then I form zinc 2 plus. That's my zag, and then there's driving force here. You see that? So copper 2 will react with zinc to form Zn2 plus. That's the first zag. The second zag is this. Copper 2 will go to copper metal. And so those are the two products of this particular reaction. And so you should see a reaction for the first one here. Sometimes, since we're not sanding the metal, sometimes the reaction is sluggish, so give it some time. You know, usually what I do is I'll go ahead and mix it, take my initial observation, and then go do something else. You know, you could do these reactions in any order that you want, and then come back to it and see if there's visible reaction or not. There should be visible reaction here because what's going to happen is the blue color is going to fade. The blue color of copper 2, and it's going to be replaced by black furry precipitate consisting of tiny copper crystals plating onto the zinc. The zinc is going to be eaten away. Okay, we're going to skip the lead. Then we're going to do some of these others. Let's take a look at silver nitrate and copper metal. Watch out for the silver nitrate. So silver nitrate and copper metal. Let's see what happens with that. So what's I have silver ions here, I have nitrate here. What's stronger, silver or nitrate? Nitrate. But there's a problem. Nitrate requires this, H plus, what do we call that? We call those protons or acid. Silver, nitrate requires acid. Is there acid present? No. And so this is like, let's say you're trying to make cookies. And the recipe calls for 1 cup of sugar, which we'll call the nitrate, and 4 cups of flour, which we'll call the acid. And let's say you're going to make cookies, but you don't have any flour. Can you still do it? No. So you're missing a key ingredient here. We need that H plus because the H plus is crucial in helping take care or stabilize the oxygens. The H plus is used to stabilize the oxygens as water. And so 2 of the oxygens go with the H plus to make 2 water, so it's 4 H pluses, and 1 of the oxygens stays on the nitrogen. That's the nitric oxide part here. And so since we don't have the H plus is missing, then the reaction should be between silver ions and copper metal. So silver ions react with copper metal. Is there a driving force? Yeah, it's downhill. Do you see this downhill? So we're good. So we expect a reaction there. All right, now we do have some acid. We have hydrochloric acid. The chloride's very weak. As far as a reducer, it's way up there, very far from lithium. So chloride we can kind of ignore. Water we can kind of ignore. So what we're looking for is the acid, H plus and hydrochloric acid, reacting with copper metal. So we're going to go H plus reacts with copper metal. That's our Zig. And then our Zag would be here. Is this uphill or downhill? This is uphill, so hydrochloric acid should not react with copper metal. There's no driving force. And so that one, the color might brighten because there's surface oxide that might get eaten away with hydrochloric acid, but the underlying copper metal itself is not going to react. Okay, any questions on this? Well, let me just do one more here. How about hydrochloric acid and zinc metal? So we have hydrochloric acid and zinc metal. Zinc metal's here. Is that favorable? Is there a driving force for that?
Yes.
Yeah, that's downhill. So we're going to go from stronger oxidizer H plus to weaker oxidizer En2 plus. All right, let's take a look at part 2A and part 2B. So what we're going to do is we're going to do something called a solvent extraction. Chloroform is like oil, and chlorine, this is called chlorine water. And so oil and water don't mix, so the chloroform ends up sinking to the bottom and forms a little plug. CHCl3 is a CCl, clear colorless liquid. And so what we're going to do is we're going to try to stopper this and then shake it. But be careful when you shake this, because some pressure might be generated and then it might pop the cork out of here, or leakage can occur through here, and then you might get some chlorine water or chloroform on your fingers. You don't want that to happen. So what we have is we have chlorine, which is non-polar, and then we have water, which is polar. And then we have this was polar here, and then we have a non-polar layer down here. So when we shake this, what we're going to do is we're going to try to get all the chlorine into the chloroform. It's not going to be possible to get all of it, but what we want to do is we want to concentrate it down here. Hopefully we concentrate enough to get a bright yellow chloroform layer. So this is called a solvent extraction. So basically what we're doing is we're taking chlorine from the aqueous phase and then transferring it to the chloroform phase. So we get chlorine in chloroform. And so here it's a light yellow. Over here it's a bright yellow. This is not a chemical reaction. This is a physical extraction. So what we should get here is bright yellow, hopefully. Here, this is going to be bright orange, and this should be bright purple. The more we extract the chlorine from the water into the chloroform, the brighter the color is going to be. All right, then we're going to do some reactions, and the way we're going to tell if a reaction occurred is by taking a look at the product. You know, we're looking for this color change. So let's take a look here at, we're going to take potassium chloride. chloroform and bromine. Chloride is colorless. Then we're going to add some bromine water. Bromine water is kind of light orange or orange color. And then we're going to add some chloroform, just a little bit of chloroform down here. And then we're going to shake this up. If the chloroform layer turns out to be bright orange, there was no reaction. However, if the chloroform layer turns out to be light yellow, then we had a reaction. The reaction we're looking at here is this. Two chlorides plus a bromine yields chlorine plus two bromides. Chlorine is going to be yellow, bromine is going to be orange. And so if we have a reaction here, then we should form yellow chlorine, and the orange color of bromine will fade away. If there's no reaction here, then the orange color stays the same for bromine, and we'll just extract the bromine here. So here we could see visually if a reaction occurs or not. But do we expect a reaction between chloride and bromine? Let's take a look. Oh, what happened? So we're going to try to take bromine and react it with chloride. Is that uphill or downhill? Do you expect any reaction? No, I expect bright orange chloroform. I don't expect any reaction. But that's not the case for all of them. And so what we're going to do is we're going to test all of them and see. All of them being potassium chloride in bromine water, potassium chloride in iodine water, then potassium bromide in chlorine water, potassium bromide in iodine water, etc. Then we'll extract and see if anything happened or not. Okay. Then we have a couple more reactions left to do after these. Let's see. So the next reaction we're going to look at is copper and bromine. So we're going to get some copper turnings. They're located in that white bucket. You see that white bucket over there with a whole bunch of copper on the top of it? You're going to cut some of those copper turnings, and you're going to put it in the test tube. And then to that test tube, we're going to add bromine water. So if we have bromine water and copper, do you expect a reaction there? Yes, this is downhill. We're going to go, copper is going, this is my zig, and then the zag is going to produce copper 2. So we're going from bromine to copper 2. Stronger oxidizer to weaker oxidizer. So the copper metal is going to be converted into copper 2. So what's going to happen is the orange bromine water should go to colorless, and then it should turn to blue. But the blue color is really hard to see, so it might just look colorless. You have to look very carefully because the blue color is very hard to detect. But hopefully it turns blue. To speed up this reaction, we're going to heat it up. When I heat it up, you could use a hot plate over there, but it's slow. I just use the Bunsen burner, and then I heat it on the soft part of the flame. Don't hold this to the cone. Hold it well above the cone. Don't point it at yourself or point it at others in case something shoots out of the top, bumps. Bumps is when a big bubble forms. So anyway, heat it gently until the orange color disappears, and hopefully you start seeing some blue. So this is our zig, and then our first zag is copper 2. Our second zag, bromine gets converted into bromide. Bromide's colorless, so we can't see it. And so what we're going to do is we're going to do a confirmation test afterwards. So after you do this reaction, what we're going to do is we're going to take that hopefully light blue, maybe colorless, liquid and divide it into 2 test tubes. So pour half into one test tube, the other half into another test tube. To make the blue color more apparent, to the first test tube, we're going to add ammonia. And copper 2 combines with ammonia to form a deep blue color. So if we see a deep blue color, that means you had copper 2 ions present. This is a test for copper 2. To the other half, in the other test tube, I'm going to add silver nitrate. Silver nitrate precipitates out with bromide to produce silver bromide precipitate. So if we get a precipitate here, that's confirmation of silver bromide. In other words, confirmation of bromide, the 2 products of this reaction. Any questions on this? Okay, this one you'll want some heat, but let's see, 3. Missing one. One of them is missing. And that's this one. This one don't heat. This one. This is 2, 2. What we're going to do is we're going to place a small amount of potassium. What's this called? Potassium permanganate. Potassium permanganate. Permanganate is a strong what? Oxidizer. It's number 4. And hydrochloric acid. So we're going to take some solid potassium permanganate and add about 3 squirts, 3 milliliters of 6 molar hydrochloric acid. So what happens if I mix potassium permanganate and hydrochloric acid? Well, potassium ions are kind of at the bottom, and chloride ions are kind of at the bottom. Chloride's up here near the bottom of the reducers. And potassium ions are down here near the bottom. And water is pretty weak too. So what we're looking at is permanganate. Permanganate is number 5. And permanganate, what can it react with? It can react with water here. It could react with hydrogen ions. There are no hydrogen ions here. It could react with chloride. Do you see that? So if potassium permanganate, if permanganate reacts with chloride, what forms? So this is Zig. What's going to form is chlorine gas. And so potassium permanganate and hydrochloric acid is used to make small amounts of chlorine gas. You can buy chlorine gas, but if you just want a little bit, you don't want to buy a whole tank. You can easily generate it. Just take some potassium permanganate. Solid is better because it's much more concentrated. Watch out, it's a powerful oxidizer, so you don't want to touch this stuff or get it on you. And then have it oxidize some hydrochloric acid or chloride to form chlorine. So this is going to generate green, yellow chlorine gas. So be careful. Do this in the hood. You don't really have to heat it. If you heat it, it may go faster. There's some hot plates there, except they let the water one dry. So don't bother heating this one. It should be fine. The final reaction here are silver and iron 2 ions. So we got silver nitrate and iron 2 sulfate. Hey, this looks like double replacement. What forms here? AB plus CD yields silver, sulfate, and iron 2 nitrate. Silver sulfate's a precipitate. So you might get a white precipitate here, but this is redox. And so let's take a look at the redox reaction from this experiment. So we have silver ions here. We have sulfate here. We have nitrate here. And we have iron 2. Where's iron 2? Iron 2 down here. But iron 2 is weird because iron 2 occurs in 2 places. Do you see iron 2 here on the oxidizer side? There's also iron 2 here on the reducer side. Okay, so as far as oxidizers go, the strongest oxidizer present is nitrate, except something's missing. What's missing? Acid. So, it's like trying to make cookies without any flour. So we'll eliminate that. So the same thing with sulfate. What's missing with sulfate? Acid. So we'll eliminate that. So as far as oxidizers go, we have silver ions and iron 2 and water. Water is way down there. What's stronger, silver ions or iron 2? Silver, so we'll ignore iron 2. So silver ions are our oxidizer. As far as reducers go, we have iron 2 and water. Water is, where's water? Well, water is way up here. Here. So it's strong, it's weaker. So we pick the stronger. Iron 2 is the strongest. It's closest to lithium, which is at the bottom. So when we have silver ions and iron 2 react, what forms? Iron 3. And so, the other product that forms is silver metal. So what should form are black. You should get like a black precipitate of tiny silver. And as the silver crystals grow, they turn silver. And so you're looking for black crystals that eventually turn out to be silver needles. And you're looking for the color. Iron 2 is green, iron 3 is yellow. So it should go from green to yellow. That's what we're looking for. All right, any questions? For this experiment, you could work in groups of 1, 2, or 3. But go ahead and get started. You can do it in any order, so do whatever reaction you want first. All right. Stop here.